So this is my fourth time recording me solving the Neetcode code about the tree, finding the valid binary search tree, and let's go. So given the root of a binary tree, return true if it is a valid binary search tree, otherwise false. And there's some constraints where the left subtree of every node contains only nodes keys less than the nodes key. It's a simple uh, binary tree, binary tree constraint. So we can start. So the simple logic is to compare the left and right value with the root. So the base logic needs to be like this, since it is a binary tree. But another thing we need to focus on is if we only consider with this base logic, we might see some edge cases where, let's say there's 4, 1, 5, 10 on the right, and if there's 3 here, base only focusing on this base logic, this tree is also valid binary tree, but in this specific problem, uh, it's not it's not about the specific problem. In the basic knowledge of binary tree, this is not a valid binary tree. Since 3 is smaller than 4, it has to go to the left side. So we also need to update the range that can go either left, right. So let's say we first set up the range as minus infinity to root as infinity. So if we go to the left, so if some node value is smaller than the root value, then we know that the left subtree starts with this root. So everything, the node that goes into the left subtree of the root should be smaller than the root. So in this case, 3 has to go to the left side here. And if in terms of the right subtree, initial state will be like this. If we care about the right subtree, we need to set up with the lower bound. So root node minus, no, not minus. So in this case, when some specific node has to go to the right side of the root node, then we can set the lower bound to root value. So this means everything on the right side should be larger than the root. So even if there's like uh, 9 here, and only caring about this, if we only care about this rule, this is only also a valid tree because the right side of the tree is larger than this root. But the thing is, 9 has to go to the right part of this root node. All right. So as we know that this uh, progress, uh, we know that if we have to go to the left subtree, we set upper bound. If we have to go to the right subtree, we set the lower. So we calculate the range of its subtree, and if there is uh, like if all nodes are in that range, we are connection. Right. So mm, first thing we need to do is definitely make a DFS by doing node, and so we need to update the the node itself on the left, and we can first think that what we're gonna give the DFS at the beginning of the stage. So we're gonna give root root left the val because in this case node is to find tree, so it has to be tree node type. Left and right can just can be the value itself because it also we only have to like compare the values to depend to decide whether the tree is a valid binary search tree. All right. So root right, and then you can just return it. Okay, inside DFS, if not node. Um, so the basic logic, which is if left is smaller than node null and right is larger than node null, we know that it satisfies, right? This is also going to be true and updating the DFS. So we need to keep track on the left and right subtree. So doing the left subtree, we said that we need to set the upper bound. So so in this case, we're gonna keep comparing with left node, right, and we're gonna set the left value. Hmm. Oh, we're gonna first move the left, and left will be same. And the upper bound should be node file, right? This is for subtree and for right subtree. You just set the node right, move the right pointer to the right, and then we need to set the lower bound as node value. Right, it's the same thing with the previous one. Right. Hmm. I think we can do as opposite. So whenever we meet, we does not satisfy the condition, we can just instantly return false here. Oh, wait a second, no. I'm not sure the syntax of it, but I guess it was like in something like this. I'm not sure which ones. STR and N doesn't mean. Oh, it is I don't know. Is it int? Not sure. Hmm. Okay. I'm gonna find it in the chat room. Um, hyphen infinity. Plot inf. Plot inf. All right. You like this? It has to be a single. Your output was null. What? Hmm. And now I should treat this. Let's make a variable that is true. Um, and valid um, false, then used to like valid. Oh, I got one right. All right. So the class return false, but it is return true. I guess this is the or. No. Hmm. Oh, I need to write this is the nominal balance. Great. Thank you. Thank you. All right. Since the code visit all the nodes, every node, only one time, it's going to be open. And complexity is going to be open. Yeah. So the important thing was about um, we should think of this edge cases where I think everyone can think of this basic logic, which is real the important part for the binary search tree. Which, like it's obvious, like left value has to be smaller and right value has to be larger. But while like validating the tree, we need to keep think that the previous node. So we need to think that the range is really important in this case, since when we only use this one, like there's gonna be a lot of edge cases for the subtrees, validating the subtrees. Yeah, so I think that's how it works. All right, thank you.